cascades.
Thank you very much for inviting me, and thank you very much for coming on such a short notice. And I'm sorry, it can be that I have problems with my voice because I was able to call yesterday. But still, so the subject is dynamic energy cascades in the theory of water waves. And the plan of the talk is following. First, I plan to introduce the notion, so very short, the notion of cascade, which comes from Richardson, and two theories which already exist for explaining energy cascades in different water wave systems. Then I show that there is a gap between two existing theories, and though I am not capable to cover all the gaps, a part of this can be covered using a new model which of a cascade which I call dynamic energy cascade, just to distinguish from the cascades which we see in wave turbulence theory, which are on kinetic time scale. So this is the origin of the name. And I present analytical results which are available already for nonlinear Schrödinger equation and a couple of modifications of nonlinear Schrödinger equation, and numerical results which are quite new. There is no theoretical proofs of something, but very interesting results about these cascades in modified Cartevert-Diffries equation. Both this and this equation, so set of equations, I am always talking about focusing equation, because main mechanism for dynamic cascade is modulation and stability. So let us begin. Yes? So, yeah, well, okay. Good. Yeah, okay. Richardson, who was an English mathematician and physicist and worked on weather prediction, he was the author of this great idea about how energy can in fact be fluxing among big bodies of water, and his idea was looking very simple. So injection scale is big, so we have big vortices or eddies. They break into smaller one, which in turn are break into even smaller one, and so we have energy flux to the another scale, which is called dissipative scale, where nothing happens anymore. So cascade dies. So it looks like a simple idea, and he made this also very clear, writing and even in his scientific book this nice verse that big wheels have little wheels which fit on their velocity, and little wheels have lesser wheels, and so on to viscosity. So this was inspired by the very funny verse of Swift's about flares, and as I see it, it was a very, very nice mixture of whirls and flares which stimulated a couple of good Russian scientists. So the first of them was Kolmogorov, who decided that the idea is worth to try to describe it in mathematical terms. And he did it. So he formulated a minimal set of assumptions which allowed him to deduce the universal energy spectrum for this energy cascade. And here you see K is the size of vertex. And the exponent, so we have power law, and exponent is universal. But of course, as it goes with every theory, there were some places which were not proven. There came some examples where the theory did not really work, or you see a cascade but it's in the wrong direction compared to what theory predicts. So there were problems, and some 25 years later Zakharov tried, yeah?
I'm confused by your statement that k is the size of the vortex.
Yeah?
1 over k, or? I mean, k is an inverse length scale.
Oh yes, yeah. Okay. And Zakharov decided to take a simpler step, so which means take the same minimal set of assumption, but to add to it some small parameter. So in Kolmogorov theory, we do not have small parameter. It is what Russians call strong turbulence. Yeah? So now we have small parameter, which I put it like wave amplitude and wave number, but this is usual for equations like nonlinear Schrödinger and modification. In the case of Carteville-de Vries equation, you will forget about k and just take amplitude as a small parameter. So it's a different scene, but the main scene is following. You have small parameter. Now you are dealing not with vortices but with dispersive waves, and the idea was that in this simpler formulation we probably can get complete theory. It turned out that this also is not the case. There are still a lot of open questions, there are still a lot of new works on it, but a theory exists. Predictions of this theory are a bit different from Kolmogorov in the following things. We do not have a universal energy spectrum anymore like this one, but the form of the spectrum depends on the form of dispersion function and on the dimension of the system. So if we know dispersion function, and if dispersion function is proportional to wavelengths in some power, then we can get analytical form of the energy spectrum, which would be different depending on what alpha we have here. For instance,
so
yes?
Depends on alpha?
Yes. Yeah. So which means that if we have here, let us say, surface water waves, it would be like k in power 1 over 2, then you have 1 beta. If we have dispersion function for capillary waves, it would be k in with alpha 3 over 2, you will get another beta. But still, you get some power law in a special class of dispersion function. So now we have two theories, both based on the main idea of Richardson. One does not need small parameter, it's strong theory. Let us put it like epsilon is equal 1. I'm not sure that it's correct, but just to get the idea. Yeah. And here we have epsilon, which is substantially smaller than 1. And what does it mean, substantially? Is in fact very important, because with water waves we can make experiments and we can measure, or we can choose this epsilon. So how we choose our wave number and amplitude and see what can happen. And there is a very interesting paper, in fact it's 2 or 3 papers by Victor Schrier and Anninkov, who investigated in all details. I forgot to put reference, but I have it, and Victor is here. Yeah, who really investigated the question how big this epsilon is allowed to be in order weak turbulence theory would be usable. And the answer is something like 0.1, perhaps 0.15 if you modify kinetic equation somehow.
But that's all. Because the reason is very simple. So in order to use wave turbulence theory, you need time scale separation, because you get different kinetic equation and different spectrum and different description at different time scales. One time scale for 3 wave interactions, another time scale for 4 wave interactions, and so on. So you need time scale interactions, and it is broken if epsilon is big enough. Then you have all types of interactions at once, 3 and 4 and 5, so you cannot use this theory. Okay, so now we know that we have strong turbulence, we have weak turbulence, and there is something in between. What is it? So, or if we put this question more precisely, is it possible to fill the gap between Kolmogorov's and Zakharov's theory? And it is obvious that we are not the first who asked this question, because if we look at the classical monograph of Zakharov, Lvov, Falkovich, then we see it's called Kolmogorov's spectra of turbulence 1, wave turbulence. And there is a citation: a volume 2 will be devoted to strong turbulence and will be a natural continuation of the first volume. A second volume intended to fill the gap was never written. So it looks like the problem is exists. It's complicated enough. So it's good motivation just to try something. Yeah? So what I'm going to talk about is a new model of what I called dynamic cascade, which happens dynamic cascades which occur in the nonlinear evolution equations with modulation instability. So as soon as we have modulation instability, we can try this approach. So in fact, it does not matter whether we are dealing with water or equation comes from optics, or we began to work in this direction already, or you just take Hasegawa-Mima equation, it possesses modulation instability, you can try this construction. And construction indeed is so simple that if somebody in some room will tell me, okay, Russians did it in 1960s, yeah, I will not be even surprised, because they did everything, probably. Yeah, but as far as I know, there are no results of this kind. The only attempt to construct, to model the cascade, energy cascade in nonlinear Schrödinger equation, as far as I know, has been done 15 years ago in a very interesting and detailed paper of Tulin and Vaseda, fluid mechanics, and afterwards there will be exact references. So what they see in experiments, they try to describe theoretically. And what is it? They see that if they generate one wave, so this is frequency and this is amplitude, then the wave is decaying in 2 sidebands, and then later in more sidebands, and this is how the physical space looks like. Their idea was very simple. Let us suppose that these 2 sidebands appear at the place where we have the most unstable mode in the interval of instability. So the main 3 things, perhaps I have to begin with this one. So the main three facts about modulation instability in the nonlinear Schrödinger equation, which we need to construct this dynamic cascade, are here. So frequency resonance condition have this form. So this is omega c is carrier wave, and delta omega is a distance from carrier wave to one side, two side bands, and we just use this notation here. So +1 it is in the direction of increasing frequency, and -1 in the direction of decreasing frequency. So what they thought and what they tried to check was following. Let us suggest that at each next step, what we have, we just double or triple this distance. So if we have delta omega between carrier wave and sideband here, so we have these two are always symmetric, yeah. But then we have once more delta omega here, once more here, once more here, and the same on the right side. So on the right and on the left side. And this idea did not work because if you make experiments, real experiments with water tank, and they did them, then you see that only two first sidebands are symmetric. But afterwards, what you see is asymmetric. So somehow, these sidebands are higher and these are lower, or the other way around, I do not remember. But it's asymmetric. And this is effect which you cannot repeat in nonlinear Schrödinger equation. You can observe it, for instance, in the Harov equation. You can even observe it in modified nonlinear Schrödinger equation, but not in this case. Okay, so now three facts which we will need further on are following. Frequency resonance conditions is this, so we see it, how it formed. Interval of instability have this form. These are all results from Benjamin Fair, so from this pioneering work where they really discovered this effect. And the next fact is that maximally unstable mode within this interval satisfies this condition. That's all. So this is very simple, and let us see what can be done with these simple facts. So these are assumptions. First, let us suppose that a cascading mode is in fact the most unstable mode, so it satisfies this condition. So it comes from experiments, you see it, you can measure it, so I would not put it as assumption, but well, okay. So I mean, I do not really feel that it's assumption, but still I'm trying just to put everything together. Okay, so this is what we have. Let us suppose further on that at the step n of cascade, the carrier mode of this next step is one of the side bands which were formed at the previous step, which means that at each step we change carrier mode, it will become smaller. We change interval of instability, it will become smaller. Now that's not well, yes, yeah. And we change the distances between the modes in the cascade. That's all. So we do not take them as Tulin and Vaseda took the same as at the first step, but we just suggest that they will be changed somehow according to the condition of maximally unstable mode, according to the assumption that our sideband becomes carrier mode at the next step. That's all. So you will be surprised how many very interesting results can be deduced immediately with a simple algebra from this thing, and how good they pass to suit to laboratory experiments. So the last, this is cascading modes, and this is assumption which makes computations easier, but has in fact can be omitted. It's just to I took it just because in laboratory experiments with water waves it is true. It must not be true in some other systems, but for water waves, what is known, it is true. And in fact, what is it? We say that the fraction P of energy transported from one cascading mode to another is constant.
Which
Wherein?
Which energy is this? Is this?
It's amplitude square.
Well, is it
Yeah.
Is it the integral over space, or is it the pointwise xt energy?
It is just amplitude square. So we take carrier wave, it has amplitude, we take square of it.
Yeah, but you integrate.
So the next, sorry?
Integrate over space.
I just measure it, no? It's discrete.
Measure the amplitude.
It
Oh,
is,
okay.
yeah.
Right. So it's,
Okay.
it's like the maximum.
Yes, yeah.
Right.
Okay, so this assumption is following. The fraction P of energy transported from one cascaded mode to the next one depends only on the excitation parameters and not on the cascade step. So at each cascade step, it would be the same amount of energy, 30% or 60% or 20%, yeah. And this is what is measured in laboratory experiments. Okay, so what we can do quickly is following. So we can call it direct cascade, where this frequency is more than previous one. This is inverse cascade, well, this frequency is less than the previous one. So we can combine them in one equation, which would be easier for computations. We see that assumption about the path of energy could be rewritten this way. And if we take this and this together, then we get a very funny but simply looking equation, because this frequency is equal to this frequency, which means that amplitudes should be the same, and amplitude of the wave with number n+1 is equal to amplitude at the nth mode multiplied with this coefficient. So that's all. And now look, we have small parameter. Small parameter is a multiplied by k. So this is a small number, and we can take Taylor expansion of this chain equation. So what we have looks like this. At this point, we can stop and make a lot of mathematics, because, for instance, I did not prove that this, you see we have infinite number of terms here. I didn't prove that it's converges to the correct solution. I do not know. I just thought like an applied mathematician. Yeah? So let us just take two terms. First will give us nothing. So minimal number of terms is here. Just cut it here and see what sort of spectra can be obtained. So, and it's here, and it is just a school exercise, and dispersion function is function of wave vector, or the other way around, wave vector is a function of dispersion. So we have integral, definite integral, we have initial conditions, we know everything, we can compute it, and let us just see. So we can compute amplitude of each cascading mode. So we can, for each step of cascade, we know all these amplitudes, and then we just compute the derivatives, and this is slope, and we have energy spectrum. Let us see what we get just doing this strange computation. So this is example for surface water waves. It's Benjamin fair, it's epsilon of this order, and we just proceed like this. And what we get, these are energies of direct cascade in each mode, and this is the finite spectrum, where constant d and constant e are completely defined by our choice of initially excited frequency of wave vector and amplitude. And we can see immediately that choosing initial conditions in such a way that one of these coefficients is equal to 0, we can get power law spectrum, no problem. In this case, if they both are not 0, then it would be deviation from power law spectrum, which is indeed observed experimentally. So we can go through a couple of more examples. This is the modification. Small parameter is bigger. Chain equation, which is a rewritten equation on the maximally unstable mode, changes. So ODE to solve changes, we can still solve it analytically, and we can still get this sort of spectrum in the system. And this is very interesting because in the previous slide, for instance, we got already, we can got very easily this spectrum omega to -5, which is very famous in the theory of water waves, like Phillips saturated spectrum, like Johannes-Webb spectrum, and things like that. So you get it just like a result of specially chosen initial conditions. And what is very interesting about this omega -5 spectrum is following. This is the only spectrum which I know which indeed is solution of the infinite equation which we got after Taylor expansion. So not just for cutted small approximation, but for the whole thing. Yeah, that's I don't know any other. So this is first example. Second, this is example for capillary waves. So it's modification made by Hogan. From this modification, this is the one particular case. So we do the same computations, we get some form for spectrum. And what is very important about this example is following. Modulation instability can be regarded as a 4-wave resonance of a special type. And capillary waves are regarded as a 3-wave system in the theory of wave turbulence. So, which means that for some excitation parameters, let us put it this way, for some initial energy distributions and for some values of energy in the system, this system can be regarded as 4-wave systems, and in some other situation it is 3-wave system. So that's why I like this example, and that's why I show afterwards the results of experimental study of the system of capillary waves, where you can measure that it's really 4-wave interactions if energies are big enough. So if we have got the form of spectra analytically, then we can play a lot of plays. For instance, we would like to know direction of cascade. We have chain equation. We have some chain equation connects frequencies and amplitudes of the neighboring cascading modes. We put expression for the spectrum into this equation and ask the question, when new frequency with number n+1 is bigger than previous frequency, omega with index n, or when is it smaller? And we will find conditions for which define direction of cascade. So if our frequencies are growing, then we go in this direction. If they are getting smaller, we go in this direction. So this is the first one. I gave here example how they look like, these conditions. For instance, if we have surface water waves, this is epsilon, this is initial amplitude, this is our parameter p, the part of the energy, and I will have to say some words about it. Yeah, and this is initial frequency. So if they are chosen in this way, then we will get direct cascade, and it will be infinite in Fourier space. If they are chosen in another way, then direct cascade will be observed only in some range of frequencies, and then we can also observe inverse cascade and things like that. Moreover, it's not only about direction, it is also, and these are very important things, it's about the termination, because both, so in Richardson, in Kolmogorov, in Zakharov theory, we always end up with dissipation. Nothing happens. But this is not the case when you are talking about dynamic cascade, and this is very clear because it is something in between. So how to go from from Kolmogorov to Zakharov, I don't know, but I know very clearly that we can begin with dynamic cascade, then we get spectral broadening, and this very quickly, because the form of dynamic cascade is usually exponential. So we have exponential decay. At each cascade step, we have two new modes, but only one of them at each step may be cascading, or it will be stopped already. So after n cascade step, we have 2 in power n modes all excited in the system, and only n or 2n modes which are cascading. So we really see that a lot of energy is spreading over spectrum, and perhaps this is the way how we can go to the assumptions which are needed to begin with wave turbulence theory. I don't know, it's an open question. There are a lot of questions which should be answered before we can really say it. Yeah. But another interesting thing is following that this dynamic cascade can also be stopped by breaking, which is absolutely not possible in both Zakharov's and Kolmogorov's theory. But from our point of view, it's really very plausible, because this is also a mechanism to put a lot of energy among the spectrum, so to make spectrum wide enough to proceed with wave turbulence theory. So we have some other effects here. I don't want to talk long about it. So experimental affirmations of all these properties and of the properties I talked above can be found, for instance, in these papers. This is about surface water waves asymmetry. They see, so this is about surface water waves, and they get energy spectrum which depends on the initial excitation, so which is not allowed to be in wave turbulence theory, but which is exactly the case when we construct dynamic cascade. And as we have seen before from the formulas for surface water waves, I predict even with this cutted equation that k can be changed from minus 4 to minus or minus 3 to minus 7. So it's very pretty good in this, so pretty good in this range. And another paper, I guess 2009 from the same group, they show also the case when cascade, so they observe discrete cascade and then it ends in breaking, not also per Fizreflest latest paper. So and what I will show you right now very shortly, this is the paper about capillary water waves. This is experiment which have been done in Australia by Misha Schatz and his group. And it's very simple, very simply looking thing. You take a plate with water. It was like 22 centimeters in diameter. And you pay $150,000 for a very big table, which is stable and can be can make this sort of excitation, and you measure. Yeah, so it's really it's a funny thing. You see, I thought it could be done in the kitchen. Yeah, it could not be done. So the data, yeah, the data showed very clearly exponential spectrum. So this is the biggest excitation energy, this is slower, and this is smaller and smaller. You see exponent is written here, and it was my suggestion. I just wanted to see it printed, because when I got theoretical results about capillary waves and cascades 0 to 4 wave interactions, it was rejected from everywhere. Just well, it's a stupid thing. It's not possible. Everybody knows that. Yeah. Yes.
Would you comment on the effect of viscosity in these very tiny experiments? Is the water deep or is it very shallow?
No, it's very shallow.
Yeah, so
Very shallow, yeah.
is it any? Do you observe any effect of viscosity?
I don't know. I don't know. I think so, yeah. Yeah, must be.
I think Kapitsa,
Yeah.
he
Huh?
included viscosity well in his kitchen table experiment.
Yeah. Yeah. It can be, I would say, how strong is effect should depend on how strong is excitation also. So for smaller, perhaps not so. I'm not sure, but it's not the point, because if you have the same rate of dissipation, you can just put it as a constant in the formula for spectrum. Yeah, so that's all. So you will have the same spectrum, even if you have your dissipation rate as a function of wavelengths, yeah, which is also reasonable sometimes. Then you can put this function into the sign, onto the sign of integral, which I wrote there. So I described this example in one of my paper. Yeah, and you will need just to compute another integral. So a form of the spectrum will change a little bit. Yeah, but the whole ideology, what I would like to say is following. There is a very simple ideology. So specific results for specific physical system can be different. This was the reason why we began with, so I began with nonlinear Schrödinger equation, but then I thought, okay, we just take something which I know nothing about, and this was modified Korteweg-de Vries equation. and really never worked with it. I have no feel, so just nothing. And we took initial conditions from the paper, which was published already, Grimshaw and company. So they observed modulation instability in modified Kartevec equation. So they wrote everything about it. They just did not look at Fourier spectrum. So this was the first experiment, just to see, okay, if this ideology is so general, because right now I do not see any, there is one restriction, and this is following. Everything what is done here is done for small nonlinearity, for small amplitudes in KdV, or for small amplitude multiplied with K in NLS. In fact, there are a lot of, so there are many very interesting papers on Kartevec, modified Kartevec equation with modulation instability and big amplitudes. I have no idea what happened there, because as far as I see now, I would perhaps be not able to get this simple ODE, which I solve to get the spectrum. So it, with this Taylor expansion, all this stuff, one should be really careful. But we have really beautiful numerical results about modified KdV. So this is experiment. These are measured data. We can see exponential spectra. We can also see here at the end some spectra which, so power law spectra, so which may be the indication that we came near enough, close enough to the wave turbulence theory. And here we can see how many percent of energy is in which part of the spectrum. So a lot of energy comes to the zonal flow mode, is it called? So it's a mode with very small k. Yeah, but then here it's energy in exponential part of the spectrum, and here we do not have any power law spectrum. Then it goes like this. So the main thing is that there is a way to check in the measured data whether we really have 3-wave interactions or 4-wave interactions. Just to measure these 3 coherence or 4 coherence, and they measured it, and they showed that in the system what they get, they have it in this range. And in general, one says that if this coherence is so about 1, then it's completely 4-wave system. It's about 1 here, then it's completely 3-wave system. And of course there are some something in between. Okay, so now we have capillary waves, and that's all for a while about nonlinear Schrödinger. And now it is modified Kartevec de Vries equation, and this is a work which has been done in collaboration with Denis Dutych. It's always a problem for me to present numerical results, where usually I do not believe in them, so I just want to prove everything. So, and this was the reason why I did not make numerical simulations myself or with a student. But Denis is really very, very good in performing just very carefully all the simulations. So yeah?
One naive question is, what is unstable here? What is unstable?
Wave?
You started with an unstable wave, but what wave? Periodic waves?
Yes,
localized wave? Or
it's a periodic wave. So you would like to see the form? I can show you. Just a moment. So we just took it from Grimshaw paper. It should be here, I guess. Where is it? Here. Okay. Yeah. Yes. Can you see it? This one here, and this is perturbation, and this is amplitude, and what we did with this perturbation, we began from 1% and we landed by 50%, just because it was unbelievably stable what we have seen. So these structures, which I call dynamic cascade. So, okay, can I take it? Yep. Okay. So where we are. Perhaps I show you video first, so that I should not go back to it. This is initial way that you write down. This cascade appears at the first time scale, time step, and it goes. This is physical space, and this is fantastic. So you you see once more, okay? I really love it because you can see that immediately all these cascading modes are here, and they are broadening, but maximum stays just like I don't know what, yeah. Just the whole time of this very space where it was born. And okay, yeah.
What was in the yellow band in the middle?
I don't know. I guess something is wrong with my computer. It wasn't there before. So I'm sorry. I have noticed it only today. So view who? Yes. Yeah. So okay. Now. Okay. So what we see here. This is series of experiments where we have a small amplitude of initial wave, something less than 0.1, and this is double as much, and we have gone as 3 times so amplitude 0.24, and the general picture is always the same. And it's only if you take a bigger amplitude, then everything is happening quickly. So you see, this is physical space, this is Fourier space, physical space, Fourier, physical, Fourier. So here you can see already the beginning of the nonlinear stage of developing of modulation and stability. Here you can see it much more quickly, so faster. So here you see that it's everything is completely unstable already, but still we see this structure. And this is not the most interesting thing, because there is something which is came completely unexpected to us. So first of all, if you begin with your wave and wave number somewhere around 0, then you only have direct cascade. But as far as you are gone far enough from K0, you suddenly see the double cascade. So inverse cascade does not exist itself, so it is always coupled with direct cascade. So what we see are these really very stable pictures. So you will never expect something like this when you see what is happening in physical space. So this in itself was a very interesting fact. But now I ask you a question. Can you do somebody has an idea what will happen if we just make computation domain in Fourier space longer? What would happen? What would you expect? So I was expected that this structure will be just what is the word? Stretched. Yeah, exactly.
Broader.
Yeah, yeah. It's not. It's not. What is happening is something which I have. You see, I have no idea what is the reason, but it looks great and important from physical point of view. So we took spectral domain 2 times as big as it was before, and what we see 2 copies of these double cascades, and each of them has about a half of energy of the initial big cascade. And if you look at the physical space, then you see, yes, we have modulation instability, yes, it is developing, yes, it is already non-linear stage, yes, yes, yes. So, the only what we can say right now about it, it's written in my conclusions in the last point. So, in general, conclusions are as following. Dynamic cascade is constructed analytically in focusing analysis and some modifications. So observed experimentally in surface water waves and capillary waves. Model predictions are in accordance. Double cascade is observed numerically in focusing MKDV, and experimental observations are not yet known. But the last thing is really very interesting. So the increase of the spectral domain in modified KDV yields the formation of 2 and possibly even more replica of the double cascade, each containing roughly 1/2 of the initial energy. Our conjecture is that the further increase in the spectral domain will lead to the appearance of more and more replicas of this double cascade. Or in other words, we will see the appearance of more and more recurrent structures sharing the total system energy. And this process may be regarded as a mechanism of the stabilization of modulation instability, just from itself. In fact, I have one idea how to compute, perhaps. I will not talk about it. Okay. So I think it's possible. At least there is one way to compute these replicas. Yeah. So this multiple cascade. But I do not know. It's just something to think about. Yeah. And at the end, it is just a list of publications. They are not all, but just something. So if you are interested, you are very much invited. Also to Linz, because I'm quite enthusiastic about this work. There are a lot of questions, mathematical and numerical, and really you can take any equation you need or you like, or you just would like to try, and check what you see. Because right now it's clear that there are some properties of these dynamic cascades which are clearly to be everywhere where we have this condition for modulation instability. This I check it for Hasegawa-Mima equation. It's always the same. So, for instance, if you have cascade for some given amplitude, yeah, you just take amplitude twice as big as it was. Do not change anything. You will see that cascading modes are moving from each other. So this distance will be grown. And it is the same. It is the same in different modification of nonlinear Schrödinger. It is the same in modified KdV. It is the same in Hasegawa. It's just the same. Yeah. But some properties are different. For instance, in nonlinear Schrödinger, of course, we are going so modified. We are going to make experiments, because now I would like really to check that we do not have these copies of double cascades. Because right now it looks like, from all simple formulas, it looks like we will have only stretched double cascade in nonlinear Schrödinger. Then it would be difference with Korteweg-de Vries. But it can be that if I get it analytically, that I have only one copy, but I get it from Cartet equation, this can be different in numerical simulation, where we have full nonlinear Schrödinger, and it can be that I just cut too early. Perhaps I have to take longer path of this Taylor expansion. I do not know, but these are the results as they are right now. Thank you for your attention. Yes?
What happens if you multiply the spectral domain by a factor of 1.5 instead of 2? Or, I mean, not an integer.
We did not do it yet.
Do you have an expectation?
I think it should depend on the wave vector where we begin with this double cascade. It should be probably the minimal distance. So first it would be stretched, because somehow it should lose its energy. So it would be stretched and then just divided into 2. I would say so, yeah. So first stretched and then divided by 2 at some point where the first double cascade is stabilized, because this is exactly what I'm going to check. So the condition for stabilization can be written out analytically also in this case, but in KdV case I do not have yet analytical formula for spectrum. So we checked that spectrum is exponential, that it's not symmetric, that when we have 2 copies, then we always have exponential decay, but asymmetric and things like that. So we checked it, but right now we do not have analytical results about it. So I would say yes, yeah. How can you lose the energy? So you should stretch it, and then at some point it just broke, and another cascade comes. Yeah. So,
yeah. So when you assume that you have a periodic wave which goes to infinity, and you have a finite tank, but it's periodic, you will never reach convergence, because the results you show have not converged. When you do something with the resolution, you would have a different result.
well, if there is limiting length of the double cascades after which it would be broken in 2, this would mean that we have some scale, and we also have sizes of tank as a scale. So the finite answer should be formulated in terms of, let us say, the ratio of these 2 scales or something like this. I don't know. These are all completely new things, like 1 month ago. Yeah, we got it. So we are just at the beginning to think about it, because I mean about this double cascade and so. Did I answer your question? Okay, yeah.
I
mean
don't
it's
think so.
Mhm.
I'm going to help afterwards.
Mhm.
Okay?
Yeah.
Go for it.
Yes, so thank you for your talk. Interesting.
You're welcome.
So this assumption in the analysis, let's say a fixed fraction p
Yeah.
of the energy is
Yeah.
cascaded onwards. Does that then imply that we are only in the deep water limit for water waves? Because we cannot have any dependence to the wave number k of the cascading energy, but only to
No, no.
just a fixed number.
No, we can just put this coefficient as a function of wave number or function of frequency, arbitrarily. The only difference with what I talked about here is that you will need to put this function onto the sign of integral, and you will have to compute another integral. What comes, you will see. But it's absolutely clear how to compute it. So I compute it just for fun. What happens if we take p like k in power 1 second or something like this? Yeah, you can compute. You can get some forms of spectra. So if there is no physics under it, there is no sense, so to say. For instance, there is in this paper here spectrum for gravity capillary waves. I also computed it analytically. It's not power law, it's not exponential, it has arctangents in the expression. Expression is big, but you can go to the limits of gravity capillary waves. They have dispersion function like this. And you will get some limiting case when alpha beta goes to 0, when beta alpha goes to 0. So you can go to capillary case or to surface waves. And these are tangents with something else here will go smoothly to the form of the spectra, which I showed how to compute here. Yeah. And so exactly this way, you just put additional function, you just try to solve this, to compute this integral, and you will see what comes. So I do not claim that in all cases, in all equations, we will always have this sort of spectra. I say if we have equation where modulation instability exists, if somebody made a good job for us, computed interval of instability and the place where the maximally unstable mode is, we can use this procedure and see what comes. So this is method. These are not answers for all specific problems, but answers are easy to obtain. That's the main message.
It's because what I have in mind is that, say, for gravity waves alone, standard Stokes theory tells what energy transfer two different wave components would give. So I'm kind of thinking about, say, how would that connect with your theory, where there's a P or where you can plug in an energy transfer?
Yes.
Could one use your approach? Get a Stokes?
It's a very good question, and I have a partial answer, which looks as following. If you take chain equation in itself, so it describes just one step of cascade, then it can be shown, it is shown by Miguel Anarata, so he made the computation, that chain equation is equivalent to exact resonance of four Stokes waves of special type, yeah, so not arbitrary, in the Harovsk equation. So he just did it, and the computation, I have the computation, I believe I included result here, because I wanted to show how this model is connected to other theories and models which exist here, but I can just send it to you. So, which means, and Stokes mode, which means that frequency depends on amplitudes. And this is exactly what we see in this chain equation. So, frequency for the next cascading modes depends on the frequency of the previous mode and amplitude. So, we can get, so from this point of view, we can say that dynamic cascade is a chain of exact resonances of Stokes waves, nonlinear Stokes waves, with frequency depending on amplitude. And this is in fact the most interesting direction to work it out further on. So, yeah.
Okay, well, thanks very much.
Yeah. Okay. Okay. Yeah.